So in the last lecture, we have started discussing Barabasi-Albert model, BA model, and we basically tried to understand whether it, BA model follows, power law degree distribution, and we mentioned that there are two ways to show that a model actually follows, whether a model follows power law or not. And these two ways, one is the continuum approach and the second way is the master equation. And in the continuum approach, we have showed in the last day that that the degree distribution for the Barabasi-Albert model basically follows power law. So we derived this equation. If you remember, Pk is proportional to k to the power minus 3, right? So today we will discuss the master equation, right, the master approach, and we will show that basically the same thing, that the power law degree distribution is followed by Barabasi-Albert model. But the way we approach this thing is little bit different from the continuum approach that we discussed in the last day. Okay. So let's get started. I am not using any slide. I am just deriving the equations slowly so that you understand each and every equation properly. So in the last class we have seen that this PD, right, P of di, the probability of a node Vi having degree di is basically di by 2mt, right. So this equation we used in the last lecture, right. But here we will use a little bit different ways, right, to basically denote the same thing. So let us define a quantity. Let n d comma t, right, be the number of nodes with degree d at time t. I hope you remember the Barabasi-Albert model, the mechanism that it follows. At every timestamp t, a particular node is coming, joining the network with a fixed degree m, okay, and each of these m edges is going to be connected with one of the existing edges based on the probability, based on the preferential attachment, and this preferential attachment is basically proportional to the current degree of a particular node. Basically indicates that if a node has higher degree, it is highly likely that the node will attract a new edge, right, compared to the node having say a lower degree. Okay. So let n d comma t be the number of nodes having degree d at time t. Therefore we define this quantity, probability of at time t, probability of a particular node with degree d, right, probability of a particular degree d is n d comma t by nt. What is nt? Nt is the number of nodes at time t, and n dt is the number of nodes with degree d at time t. Okay. So in the continuum approach we use this equation, right? Can we write the same thing in a different ways? Can we write the same thing, probability of of a degree d? Can we write in this ways? D times PTD divided by sum of all d, right? Let us write d dash, okay, PT d dash. Think about it. So this is the degree and this is the probability of that particular degree at particular time, okay, and the denominator is sum of all the degrees but proportionately, okay. So the denominator is kind of a weighted average, right. Say you have 5 degrees, right, 1 2 3 4 5 for example, right. So your d dash varies from 1 to 5 and you have PT d dash, right. Say for degree 1 this is 0.1, this is 0.2, 0.2, this is 0.5, this is a 0.4, and this is 0.1. So the sum would be, the denominator would be what? 0.1 times 1 plus 0.2 times 2 plus 0.2 times 3 plus 0.4 times 4 plus 0.1 times 5. This is basically, weighted average. Okay. So the denominator is essentially, the average degree of a node. Average degree of a node in the particular network. Okay. So so let us just focus on the denominator. Okay. So d dash, so d dash is all the, d dash indicates, d dash is basically the index indicating the possible degrees that you have in the particular network. pt d dash, okay, this is basically average degree. Okay. So average degree is what? So sum of degree is 2 into number of edges, so 2 into number of edges, and since this is average, right, so sum of degree is essentially average degree into number of nodes, right, number of nodes. I am basically moving this thing in the denominator, so then this is going to be the number of nodes, right, number of nodes at time t, number of edges at time t, right. What's the number of edges at time t? So at every time m number of edges are coming in, so number of edges at time t is m times t, so 2mt. And what's the number of nodes? Number of nodes is basically t, because at every time stamp there is only one node coming in, so this is 2m. Okay. So the denominator is 2m. Now let us define two quantities, right. The first one is called outflux. Okay. What is outflux? Outflux is the number of nodes, right, which had degree d minus 1, right, and upon say addition of the node. So we are interested in the situation when a particular node is added. Okay. So when a particular node is added, the degree will change, right, the degree of other nodes will change. Now we are interested in only those nodes whose degree is d. Okay. So when a particular node is added to the system, what would happen? So there are nodes which already have degree d, right, and due to the addition of this node, it may happen that some of the nodes will basically acquire edges. Out of these m edges, at least one edge will be acquired, and those nodes whose current degree is d, right, due to the addition of one additional edge, the degree will basically become d plus 1. So those nodes will not be counted when we calculate the number of nodes with degree d at time t, because those nodes will have degree d plus 1. So we call those nodes as the outflux. Okay. They are actually moving out of the system. I mean, the system is a system that we are considering at current timestamp. Okay. So number of nodes which had degree d, which has degree d, sorry, it is d, not d plus 1, which has degree d, and upon addition of the node, their degree increases to d plus 1. Okay. Therefore these nodes will not be counted in n of d comma t. Okay. So this is outflux. Now similarly we have influx. So influx constitutes those nodes whose earlier degree was d minus 1, and due to the addition of this new node, their degree will become d. Okay. So number of nodes which had degree d minus 1, and upon addition of the new node, right, the same phrase here, their degree increases to d, right, and these nodes will be counted, will not be counted here, will be counted here in dt. Okay. So we will try to analyze, we will try to understand how many such nodes are there in the influx, how many such nodes are there in the outflux. Okay. Now, so here we have seen that Pt is d times Ptd divided by 2m, right, probability of particular degree d. So now, since remember, so when a particular node comes in, so one of the edges, one of these m edges will join, will basically connected to a node. It will not happen that the same node will again be chosen for another edge, right? There will not be any parallel edges, right? So the number of nodes of degree d that gain at least one edge, right, due to the addition of the new node, right. So we are interested in the number of such nodes which will gain at least one edge, right. So m number of edges are coming in, and what is the probability that a node d, a node with degree d will gain an edge, and how many such nodes are there? So there are, so Pd is the, Pd is the probability of nodes with degree d, right. You can also say that Pd is the fraction of nodes with degree d, right. So out of these m edges, how many edges will going to be attached to nodes with degree d? This many. Okay. So I replace Pd by this one, so this is going to be d, right, Ptd by 2, m and m will cancel out, right. So so remember this particular term. This is basically saying that when a new node joins in, how many nodes with degree d will gain an edge, okay, gain a degree or whatever, an edge. Now let us denote another quantity. So many notations are being used. So it's very important that you basically list down all the notations that we are following, so that whenever those notations are referred, you can easily understand. Okay. So let us denote another notation p sub d comma n. What is this? This is same as Ptd, probability of a node, probability of a degree d at time t when when there are n nodes in the system, in the network. So when there are n nodes in the network, what is the probability of a node, what is the probability of a degree d? Okay. So now let us write, so now let us try to understand the number of nodes with degree d, right, at a particular time t. So when this new node comes in, right, what would happen? So, the number of nodes will become n plus 1, right. So, at n plus 1, so when the number of nodes is n plus 1, how many nodes are there with degree d? So, P of d n plus 1 is what? P of d n plus 1 is the probability of a degree d when the number of nodes is n plus 1, or the probability, or it is basically a fraction. So, fraction of nodes with degree d when the number of nodes is n plus 1. So, what is the total number of nodes with degree d when the number of nodes is n plus 1? N plus 1 times this fraction, right. So, this is kind of an influx, or this is kind of the quantity that will contribute when you measure the number of nodes with degree d, right. And we need to subtract, right, this quantity in d n. What is this? This is the number of nodes with degree d when the total number of nodes was n. When this new node joins in, there were already some nodes with degree d, and those nodes will now become d plus 1. So, those nodes will now be, now we will not contribute to the total number of nodes with degree d anymore. So, how many such nodes are there? So, total number of nodes is n, and the fraction of nodes with degree d when the total number of nodes is n is this quantity. So, this plus this is the net quantity of the number of nodes that we should consider now. Okay. So, in other words, this is basically influx minus outflux, right. Now, this is one way of writing influx plus outflux. Now, we can also write influx in a different manner. We can also write influx, based on this equation. Okay. Now, what is influx? Influx is essentially, now remember, we have already renamed this notation, right. We have already renamed it by d into p d comma n by 2. So, this was renamed here. Okay. So, what is influx according to this one? Influx is when the system had n minus 1 number of edges, n minus 1 number of nodes, and let me go back. So, when the system had n number of nodes, how many nodes were there with degree d minus 1? So, this is the fraction. So, p d minus 1 comma n, okay. P d minus 1 comma n is the fraction of nodes with degree d minus 1 when there were n number of nodes in the system, okay. And what is the total number of such nodes? Times n, So, we have already seen that the total number of nodes with such degree is this one, right. So, let us write in there using this equation. So, if this is d, this is d, so this is d minus 1, this would be d minus 1. So, this quantity indicates the number of nodes. If you look at this phrase again, number of nodes with degree d minus 1 that gain at least one edge due to the addition of this new node. Now, this will contribute to the quantity that we are interested in. So, this is influx, okay. And what is outflux? Outflux is P of, right, d comma n, right, the number of nodes with degree d when there were n number of nodes in the system, right, those will basically gain one edge, right. So, the number of such nodes is this one, okay, of course by 2. Now, if this is not understood, so we basically try to write influx and outflux in two different ways, one based on this quantity, other based on this quantity. Okay. So in the asymptotic label, label, meaning when n tends to infinity, okay, all these notations, right, these small notations like p of d n plus 1, right, p of d n, right, all these notations, these two things would be same. This would be p of d when n tends to infinity. So we replace these by p of d. So now the modified equation is this one, n plus 1 pd minus n pd is d minus 1, right, p d minus 1 by 2 minus d pd by 2, because in the asymptotic label when n tends to infinity we will ignore the n at every place. Okay. So now if you solve this equation and if you try to get the values of pd, you will get pd is d minus 1 by d plus 1, right, p d minus 1. You see here this npd and npd will cancel out, so n will vanish and you will get this equation. Okay. Now this equation is true when d greater than m. What about d when d equals to m? D is the degree and m is this one, the number of edges that are attached to a particular node, right. When d equals to m, what would happen? When d equals to m, right, so this pd will become pm, right. So I will write this equation again in a different manner. So this will be n plus 1 ppm minus n pm equals to, now think about the influx. So it is basically saying that what would be the number of nodes with degree m when a new node comes in. The number of nodes with degree m. Okay. So what's the influx? Number of nodes with degree m. How many such nodes are there with degree m when a new node comes in? 1, because the node which is coming, that node has degree m. So the influx would be 1. And what would be the outflux? Outflux we do not know, so we need to compute. So outflux would be, let us look at this quantity again, right, or whatever, this quantity. So this would be m times pm by 2. Okay. So here also if we calculate, if we just calculate the value of pm, you will have a pm equals to 2 by 2 plus m. Now we have two equations, when d greater than n, when d equals to m. When d greater than n, you have pd this one, when d equals to m, you have this one. Now we need to solve this this equation. You see this is a recursive equation, the equation 1, right. Pd is dependent on d minus 1, d minus 1 will depend on d minus 2 and so on, right. So let us unfold it now, okay, and we stop when d equals to m, because at d equals to m we have a non-recursive value. So Pd equals to d minus 1 by d plus 1 p of d minus 1. Okay. This is, so I am replacing d minus 1, right, in these equations we will get d minus 1 d minus 2 by d plus 1, I think I made a mistake here, so this should be 2, d minus 1 d plus 2, okay. So this would be 2. So this is d plus 2, d plus 1 and p of d minus 2. Okay, and we basically do this same kind of replacement again and again until unless we see this one d minus 1, d minus 2 dot dot dot, right. We basically do the same replacement until unless we get m. Okay, and in the denominator we have d plus 2, d plus 1. So what would the last value here? Remember, when this is when this is d minus 1, this is d plus 1, right. So when so the difference between this and this is 3. Okay, now when this is m, this would be m plus 3. Okay, and this would be pm, because here d minus 2, here also d minus 2. This is m, this is m. Okay, so now what we'll do, we'll replace pm by this one. So we'll have let me just replace it here. So we'll have 2 by m plus 2. Okay, so now if you look at it carefully, so let me break it further. So you have d minus 1, d minus 2 dot 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 m, right. In the denominator you have d plus 2, d plus 1, d minus 1, d minus 2 dot 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 m dot 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 m plus 3, right, and m plus 2 also, and we have 2 here. So this part m into right. So this part and this part will vanish. Okay, but we need to multiply this one right here. So this would be m. If you multiply here m and m plus 1, right, then this and this will vanish, right. So we'll have 2 m into m plus 1 divided by d plus 1, d plus 2. Okay, so this is PD. So PD is 2 into m plus 1 into m and d into d plus 1 and d plus 2. Okay, so m is constant. If you look at the denominator, this is d cube, right, d times d plus 1 times d plus 2. So you will have a component which is d to the power 3. So PD will be proportional to d cube, d to the minus 3. Okay, this is proportional to 1 by d cube, meaning it is proportional to d to the power minus 3. So we will see here that the degree distribution here also follows a power law, and the coefficient is minus 3, and the same coefficient we obtained in case of when we used continuum approach. Okay, so the proof is, this approach is little bit tricky, but I suggest if you think about it carefully and if you derive it on your own, you will understand it. Okay, so this is all about Barabasi-Albert model. Now if you look at the limitations, right, limitations of Barabasi-Albert model, the major limitation is that we consider only one node at a time when increasing the network. So at every time only one node is joining in, right, but in real world there are multiple nodes that can join at the same time. Okay, and when multiple nodes join, when multiple nodes join in the network, we do not know how to make them, how to come up with a sequence that, okay, this will be considered first, this will be considered second, and so on. So this is not clear. Okay, and this is a linear growth model because every time only one node joins, therefore the growth will be linear with time. So if we see T and number of nodes in the system, we will see it like this. But real world network does not follow this linear growth kind of pattern. Both the models, both the approaches, continuum approach and master equation, we observed that the coefficient of the power law is -3, 3, right. We observed that Pk is k to the power -3. So, this is 3 is gamma. But in the real network, real world case, gamma actually varies from 2 to 3, even 1 to 4 sometime, right. So, we won't be able to get a variety of such scale free graphs using Barbour-Albert model, because Barbour-Albert model, according to Barbour-Albert model, the coefficient is always fixed. BA model does not capture the temporal decay of preference of a node. What does it mean? So, as the time goes by, what happens is that a node actually starts decreasing its importance. Okay. Now, think of movie actor, actress, right. As they become older and older, their preference may decrease. I am not saying that this is true, but in general their preference will decrease. Okay. So, this kind of temporal decay of preference is not explicitly present in the Barbour-Albert model. And the last problem is that there is no such factor of competitiveness, right. What does it mean? It means that when a new node joins, it does not have the power to compete with others. Now, think of a system, think of a again scientific research collaboration kind of a system, where when a new scientist joins in, the scientist may be brilliant, right, and the scientist, although he is young, but he or she has the capability to compete with other researchers. Similarly, movie actor, actress, when a new actor or actress joins, right, he or she may have better performance ability. Okay. But according to Barbour-Albert model, you will have to survive for certain point in time in the system, so that you gain certain age and your degree will increase, and then your preferential attachment probability will also increase. There is no such competitiveness or competition that as soon as a new node joins in, he or she has the node has the capability to compete with others to gain new edges. Okay. So, these are the problems of Barbour-Albert model. Later on, many such advanced models have been proposed. We will not discuss those models in this particular chapter. I will try to, in the next lecture, I will try to give you a very brief of the other such approaches which basically try to address these limitations. Okay. With this, I stop here. Thanks.